Let's first look at the policy iteration method for finding the optimal policy. The structure of this iterative method looks like this. We start with some arbitrary policy pi. Then in every iteration, we first evaluate this policy, the current policy. For this, we just use the formula that we know for evaluating the value of a policy and compute the value vector. Next, we try to improve the current policy. And to improve, we use Bellman optimality equations. So we compute for every action the expected immediate reward in every state plus the expected value of the next state times the discount factor gamma, and the new policy takes the action that maximizes this expression. Choosing the new policy in this way always guarantees that the value vector of the new policy will be greater than the value vector of the old policy, or at least as good as the value vector of the old policy. This process stops if we find in an iteration a new policy which has exactly the same value vector as the old policy. At this point, we know that the new policy or the old policy satisfies the Bellman optimality equations. So we know that the value vector of the policy we have is equal to the optimal value function, and the policy is an optimal policy. To understand how the policy iteration method works, let's go back to our favorite example of a simple MDP with 3 states and 2 actions. The 3 states are the fallen state, standing state, and moving state of a robot, and the 2 actions are so-called slow action and fast action. What happens when the robot takes a slow action is shown by the black arrows here, and what happens when the robot takes a fast action is shown by the green arrows here. Now let's try to find the optimal policy of this MDP using policy iteration. The policy iteration method starts with some arbitrary policy, and here I have chosen the arbitrary starting policy to be the one that takes always the slow action in all states. And here I've shown the expected immediate reward for this policy. The immediate reward for the policy of taking slow action is clearly 1 in both moving and standing state. For the fallen state, the expected reward of taking slow action is a combination of these 2 scenarios, which is minus 0.2. P pi is the transition probability matrix for this policy, which is the transition probability given by the black arrows on all states. From fallen state, the probability is 0.6 of going to the fallen state, 0.4 of going to the standing state, and 0 of going to the moving state, and so on for standing and moving state. The gamma that we look at here is 0.1. The aim would be to find the optimal policy to maximize the sum of expected discounted rewards with this gamma factor. So in iteration 1, we will start with the starting policy of always choosing the slow action. Now the first step of the policy iteration method is to evaluate the current policy, the starting policy in this case. To evaluate the policy, it computes the value vector using the inverse matrix formula, and I have just written that for you here. It comes out to be this vector here. Then the policy iteration method will try to improve this policy, meaning that it will try to choose some other action for every state if another action seems better according to this expression. Now for the fallen state, there is only one action available, the slow action. So let's see if we can improve the actions in standing or moving state. For standing state, the slow action value is 1.11 as given here for the current policy. And that is going to be the same if we try to evaluate this expression again by the Bellman equations. For the fast action, if we use this formula and compute what happens for the fast action, the expected immediate reward for the fast action in standing state evaluates out to be 0.6 times 2 plus 0.4 times minus 1, and that's 0.8. Gamma is 0.1. The transition probability for the fast action in standing state is 0.4 probability of going to the fallen state, 0.6 probability of going to the moving state, and no probability of going to the standing state. The current V pi is given by this vector right here. So we just substitute it here, and we evaluate this whole expression, and it comes out to be close to 0.86. So we can clearly see that the slow action is still the better one to take according to this expression. So in the new policy, we keep the standing states action as the slow action. Next, we try to see if there is a better action available for the moving state. There are two possible actions. We first evaluate the slow action. This expression for the slow action will come out to be the same as before because current policy is using slow action. For fast action, we evaluate this expression. The expected immediate reward is 1.4, as we can see from here. With 0.8, it is +2, and with 0.2, it's -1, so that's 1.4. Gamma is 0.1. The transition probability vector is given by this because with 0.2 probability, it goes to the fallen state, and with 0.8 probability stays in the moving state. And this here is right here is V pi. When we evaluate this expression, it comes out to be 1.48. So this is better than what we had before. So we decide that in a new improved policy, we should be taking fast action for the moving state. So now we have an improved policy, so to say, which has decided that it will keep taking the slow action in the fallen state because that's the only action available in fallen state. In the standing state also, it will keep taking the slow action as before, but this new policy will take fast action in the moving state. The next iteration, iteration 2, starts with this new policy. The new policy, to summarize, is that it takes fast action in the moving state and slow elsewhere as before. For this new policy, we again compute the vector of immediate rewards. It is same as before, -0.2 in fallen state, same as before 1 in the standing state, but in the moving state it has changed, it has become more 1.4. We again formulate the transition probability matrix by looking at the correct arrows according to the action taken. And then in the beginning of the state, we evaluate this policy by computing the value vector by our inverse formula, and these are the numbers that come out to be. You can compare it to the value vector that we computed in the previous step, and there the values were smaller than what we have before. So this shows the claim that when you go from one iteration to next, the value vector is at least as good as the previous iteration. And in fact, we see a strict improvement here, and that's why we didn't stop. Now we again try to improve this policy by choosing in every state the action given by this maximizer of this expression. Again, we first evaluate the standing state and we see if we can improve the action there. We are currently taking the slow action for which this expression will evaluate out to be close to 1.15. We try to see if we should take fast action. Will that be better? So again, we evaluate this expression here. Expected reward, immediate reward is 0.8, gamma times the probability vector, and then V pi coming from here. And this evaluation comes out to be 0.88, clearly the worse. So we keep taking the slow action. Now we try to see if there is a better action for the moving state. First we evaluate the fast action, this expression for fast action, and it will come out to be the same as the current value because we are taking the fast action right now in the current policy. We evaluate it for slow action then. The expected immediate reward is 1 for slow action. Gamma is 0.1. The transition matrix for transition probability vector for the slow action is this because it always stays in the same state for the slow action, and we get the V pi from here. And this evaluates out to be close to 1.15, clearly the worst, so we keep taking the fast action. So to summarize, in the end of iteration 2, we find out that we want to keep taking the slow action in the standing state and fast action in the moving state, which is the same policy as the old policy. So the value vector has not improved strictly. It is the same as before, the policy is same as before, and this is our stopping condition. So we have found the optimal policy for this MDP in 2 iterations. The optimal policy is to take slow action in both fallen and standing state and fast action in moving state. The optimal policy we have found was for gamma equals 0.1. In fact, if you use a different gamma which represents different weightage given to the future rewards, you'll find a different optimal policy. I would encourage you to try it for different values of gamma like 0.9, 0.99 and so on, and see if the optimal policy changes.